All right. Can everybody hear me? Can everybody hear? Can everybody hear me up there? We have a short announcement about the hackathon. Where's that person that wanted to make that announcement? Not here. All right. One, two, three. Yeah, that's good. So last time we talked about pushdown automata, context, and context-free languages are based on grammars. And so we're going to chapter 2 of the book, context-free grammars, context-free languages. We said that the grammar is a set of variables, a set of production rules, and a start symbol. And basically you can take the start symbol and create strings out of it that are made of terminal symbols only. And all such strings that you can make beginning with the start symbol are the strings of your language. And the language is context-free if and only if there's a context-free grammar that generates it. So we gave a lot of examples. We said that, for example, sigma star can be generated with a very simple grammar, SA, SB, or epsilon, where S is the start symbol. That can give rise to any symbols in any order, which makes all strings in sigma star. And then we said the set of palindromes that reads the same as backwards as forwards. Another simple grammar, S goes to ASA, or to BSB, or to A or to B. And all palindromes can be formed this way by shooting off an A and a B to the right to the left simultaneously in lockstep. And so you get a palindrome at the end. Another example is a set of all well-balanced parentheses. Again, here's a context-free grammar. It's pretty short that generates all possible ways of well-forming parentheses with proper nesting. And a set of all regular expressions taken as strings can be generated by a context-free grammar based on that. And we talked about ambiguity. We said ambiguity is not great either in language or in programming or in speech. And whenever you have ambiguity, you should try to get rid of it or have a grammar that's not ambiguous. By the way, we'll take roll today, so put your name and computing ID sign. So ambiguity could be great in art or even in music, but not so good in formal languages. So language is ambiguous if and only if there's two or more ways to derive some particular string. Could be any string. Not every string has to be ambiguously derived, just one, and the whole language becomes ambiguous. So for example, the language is consisting only of the empty string. Epsilon can be derived using this grammar. S goes to SS or to epsilon, but there's lots of ways to derive epsilon in this grammar. In fact, an infinite number of ways. So this grammar is not just ambiguous, it's kind of infinitely ambiguous. Here's a much smaller grammar. S goes to epsilon, and that's it. And that generates the empty string as a language. And that grammar is not ambiguous. It's a unique single way to generate the empty string there. So that's a simple example of how to get rid of ambiguity if you have an ambiguous grammar. Come up with a shorter grammar, or not necessarily short. The grammar may even be longer, but it will not be ambiguous if that's possible to do. Now, in general, it's not always possible to do that. We'll talk more about that in a second. L is a language A star, so here's one grammar, SS or A or epsilon. But that's ambiguous. Here's a grammar that's not ambiguous for the same language, A star. Well-balanced parentheses. That grammar was ambiguous because there's two ways or more to derive parentheses, open paren, close paren. Here's one way, here's another way. And two derivations are different if they have different form, if they have a different derivation tree. You can think about a derivation as a tree, right? Just like when you parse a sentence in English into verb and adjective and different parts of speech, you have some sort of a parsing grammar tree, and same thing here. Here's an analogous grammar that generates still all well-balanced parentheses, but this one is not ambiguous. It's not completely obvious that this grammar generates the same language as that grammar, but you can prove it. Again, the way to prove two sets are the same, and languages are sets after all. To prove the two sets are the same, you show that one is a subset of the other, and the other is a subset of the first separately, and then that makes them equal. And that's a general conclusion or result. Proof technique for equality of sets. So a grammar is ambiguous if some string in it has two non-isomorphic derivations. It turns out that, as we saw already, some context-free grammars are ambiguous. We've already seen several examples of that. But it gets a little worse than that. Some context-free languages are inherently ambiguous. In other words, inherent ambiguity means that no matter what context-free grammar you come up with for that language, that grammar will necessarily be ambiguous. There's no way to express that language using a non-ambiguous grammar. At this point of inherent ambiguity, the problem of ambiguity is not a problem of the grammar. It's a problem of the language itself. So it's kind of a worse form of ambiguity. So it's two different forms of ambiguity we're talking about here. Okay. And the first one is fixable. If the grammar is ambiguous, maybe you'll come up with another grammar that's not ambiguous. And often in practice, that's not hard to do. But you should also be aware that some languages, some context-free languages, are inherently ambiguous. And here's an example of a language that's inherently ambiguous. A to the n, B to the n, C to the m, D to the m, union with A to the n, B to the m, C to the m, D to the n. So here the n's and m's are nested this way. In the other case, they're nested this way. Okay. So it's one nesting like this versus a nesting like this. And it turns out it's not easy to prove. We won't prove it here. It'll take too much time, and it's not worth it. But I'm giving you an example of an inherently ambiguous context-free language, which is the union of these two context-free languages. So is this language, A to the n, B to the m, C to the k, where either n is equal to m or m is equal to k. Either the first two exponents are the same or the second two are the same. In other words, number of a's must match a number of b's, or alternatively, the number of b's must match a number of c's, or both. Because it's an or, it's not an and. So that's a context-free language, but this was a grammar for it, but every grammar for it will be ambiguous necessarily. So people can prove these things, and people have proven these things. So you should just be aware of that. So ambiguity is something that you should avoid, not just in everyday speech and good communication with other people, but in programming language design and all sorts of syntactical structures and so on. Now, this brings us to pushdown automata. So we're entering section 2.2, roughly page 109, 110, 111. A pushdown automata is basically a finite automata with a stack. So it has all the features of a finite automata, plus it has a stack that it can push things onto and pop things from. Yeah. And the stack can act as a storage, right? So it has a finite set of states, like a finite automata. It has an input alphabet and a stack alphabet that could be different or the same as the input alphabet, because a stack has symbols written and read from it too, pushes and pops. And it has a transition function. A transition function is a little more complicated than that of a finite automata because it can change states not just based on what state you're in now, but what the top of the stack looks like at this moment, the symbol at the top of the stack. So that transition function can depend on that too. So the number of states that this can depend on is represented by this Q, and the stack is represented here, the top of the stack. And the input alphabet, of course, it also depends on what's in the input, just like a finite automata, but also on what's on the stack, the top of the stack. And it has non-determinism built in this time. Finite automata didn't have non-determinism built into them. We added it as an afterthought later, and we showed that non-determinism in finite automata is equivalent to deterministic finite automata. And what was the proof technique there? That we showed that non-deterministic finite automata could always be converted to a deterministic finite automata. Anybody remember the proof technique? 2 words? Close. Generalize it a little more. Power set construction, right? Any number of states can be represented. That's a power set of a state set. Yeah. Here, non-deterministic push-down automata in this computation model can do more than deterministic ones. There's no equivalent of a power set construction here. And the reason is, if you try to generalize power set construction to this scenario, you have to take not just all combinations of states, but all combinations of stack contents. But the stack could be arbitrarily large. So there's no end to the number of possible states plus stack combinations, and the power set construction will never finish. And there'll be an infinite number of situations that it has to take care of, and it'll explode out of finiteness into infinity, so that's not good. And more formally, we'll give examples of languages that are non-deterministic context-free, but not deterministic context-free. They can be recognized by non-deterministic push-down automata, but they cannot be recognized by any deterministic one. So this is why there's a power set construction here, or power set notation here. The result can be any one of a number of states and stack pushes and pop combinations at the top of the stack. So we're not going to a unique next state and push or pop. We're going to an arbitrary number, fixed, finite, but arbitrary number of pushes and pops, non-deterministically. So non-determinism is built into the very definition here because it can do more. It's a superpower here for push-down automata. So just so you're aware. Initial state is similar to finite automata. You got to start somewhere, and that's a unique starting place. The computation got to start somewhere, and that's where it starts with Q0, purple color-coded. The final states, like a finite automata, are just a subset of all the states. And so the push-down automata is a 6-tuple, right? The finite state set here, the input alphabet, the stack alphabet, which may or may not be the same as the input alphabet. You have that option if you want. The transition function, the initial state and the final states, plural. Most of the action, of course, happens with the transition function, just like in finite automata. All right, the rest is pretty straightforward. So push-down automata are non-deterministic, so we're emphasizing that here again, what I said a couple of minutes ago. Any questions about what a push-down automata is? Basically a finite automata that also has a stack. In the third homework that's out right now, you'll have a JFlap exercise to actually implement some simple push-down automata, see how it works, test it on different strings. Nothing too onerous, just so you're familiar with how to construct one and watch one work and see why and how it works and so on. Okay, so a push-down automata can use its stack as an unbounded but access control manner. So it's a LIFO, last in, first out. So a stack, whatever you put the last thing onto the stack, that's the thing that's going to be popped out of the stack when you pop something from the stack. So it's like trays in the cafeteria. You keep putting trays on this spring-loaded rack, big stack of trays, and you always take the last tray that was somebody put on there. So the first tray that you put on there will be used or taken out last, so because it's a stack. Line at your supermarket, it's not a stack. What is it, rather? Line at the bank or a supermarket? It's a queue, right? It'd be kind of disturbing to customers if the line at your supermarket or the bank was a stack. They'll be very angry. Think about it, because the last person coming into the line will be first served, and everybody who came in first will be waiting forever until the stack is finally emptied. So they'll be first in, first out for a queue, but stack is last in, first out. So pushes and pops are what access the stack. So there's a picture. The finite control is over here with a set of states. There's the initial state in purple right there. The set of final states is all these all these red double-circled final states. Again, all color-coded. The initial state is purple. Final states are blue. The transitions, final states are red, and the transitions are always in blue. At least I try to be consistent about that. So there's a stack. An A was pushed, a B was pushed, another A was pushed, and right now the machine is looking at that A. There's a stack pointer always to the top of the stack. That's where you push and pop from. And the stack alphabet and the input alphabet may be different. We already mentioned that. So here's the input alphabet made of zeros and ones. The stack alphabet is made of A's and B's. That could have been the other way around, or both input and stack alphabet could be A's and B's and zeros and ones, if you'd like. It's up to you, the pushdown automata designer, the programmer. And when you reach a final state, regardless of where you are in the input, you can say, I accept. So the thing accepts if and only if it reaches some final state. You don't have to continue to process the input or continue to clear out the stack, empty the stack or anything. Although you could define acceptance as when the stack gets completely empty or some other way. But there's lots of ways to define acceptance here because there's more going on than a finite automata. But let's just say if you enter a final state, you're good. You accepted that string in the input. So you can make a PDA deterministic by restricting the transition function to be a particular single unique next state and push pop, command to the stack, in which case that 2 is missing. That 2 that we had in the previous slide right here is missing, and instead we just have that exponent here, the Q crossed the transition, the Q crossed the stack push pop thing. So, but that's now a deterministic pushdown automata, and just again to emphasize, there's things that a non-deterministic pushdown automata can do that a deterministic one cannot do. For example, recognizing palindromes, WWR, and a whole bunch of other things that are context-free. Non-deterministic, you can recognize them, but not with a deterministic pushdown automata. So, again, to summarize, every time the input is advanced 1, the machine changes states, just like a finite automata would. And the top symbol on the stack is replaced by some other symbol of the stack alphabet, either by an epsilon, which means that symbol now is gone, or by a pair of symbol itself and some other symbol, which means there's now one more symbol on the stack. If you'd like, you can replace the top of the stack by some string rather than a symbol, if you'd like. Right? So that string could be either epsilon, which means implicitly it's a pop. If that A is replaced by an epsilon, then A is gone from the stack. The thing about the stack is one long string. Right? And the read-write head, the push-pop head is pointing to the end of the stack, to the top of the stack. And if you substitute on a transition something bigger, like a ABC, or an AA or a BB, now that A will be gone, and instead it will be a BB, which means you've pushed something to the stack. So in one transition you can do a pop or a push, if you will, or neither one, nothing at all. If you replace the top of the stack this A by another A, then you haven't touched it, and that's a perfectly valid transition. Question?
Oh, are we allowed to have transitions that don't do anything?
Yeah. So it's a good question. So you can have a transition that doesn't modify the stack at all. Of course, not modifying the stack is equivalent to replacing the A by an A. It's another way of thinking about it, right?
Well, wouldn't that change how we move the base into the stack?
Well, so if you want to empty the stack, you want to replace the A by an epsilon, and then it'll point you at the B, and then the B by an epsilon, and replace this A by an epsilon, and then it'll quickly empty the stack. You spin around and just pop and pop and pop, and don't do much other than that. Then it'll empty the stack pretty quickly. Or if you want to push a lot of A's, replace the A by an AA, and keep doing that. That'll just push a lot of A's to the stack. So however you want to think about it, it's fine. But these are kind of like atomic operations. It'd be, you don't want to say, well, write Shakespeare's Hamlet to the stack in one fell swoop. That's a pretty long string. Although technically you could, in terms of definition. Why? Because if you were allowed only one character at a time, well, then have, 10,000 transitions, maybe 500,000 transitions, each one pushing another character from Hamlet, just in the right sequence, so that at the end, the entire play, Shakespeare's Hamlet, is on the stack. And that's just one long set of state transitions, one character at a time. So that will be equivalent. So as a shortcut, we'll say, okay, in one fell swoop, just put the entire string Hamlet on the stack, and that's that particular transition. Now, that string now is part of the definition of the transition function, the delta transition function. Any other questions or comments? So, creating these machines is very similar to what you've been doing so far, creating a finite automata. How do you do it? Well, have a set of states, have the right transitions that kind of do the right things to accomplish whatever goal you're trying to accomplish. It's a lot like programming. In fact, it is programming. It's kind of low-level, primitive kind of programming, like you're programming a machine in machine language or something. But it is programming, and fixing it when it doesn't work is debugging. It's exactly what it is. So if this kind of smells like programming when you're using JFlap and trying to figure out the right machine with the right states and have the errors in it, fixed so it does the right thing, it doesn't glitch, that's debugging, pure and simple. Yeah.
Can you explain what you said about acceptance again?
Yeah, so if you enter a final state in this PDA model, the initial input, the input string is accepted. And that string is part of your language, the language of this PDA, the language accepted by this PDA. So it's a lot like the finite automata. If the finite automata processes the input string and ends up in the final state, that string is in the language. If it processes the input string and ends up in the non-final state, that string is not in the language. So it's an if and only if. Here, you don't necessarily have to exhaust the entire string if you don't want to. Why? Because it's equivalent to exhausting it. Let's say you're halfway down the string and you say, I accept. It meets my criteria for membership in the language. Well, what you can do then is have another machine that does that, plus right after he decides to accept, he doesn't quite accept right there and then, but goes over here to some other side state that then just flushes the rest of the input, and maybe even flushes the stack if you want, and then accepts. So all these modes of acceptance by empty stack, by final state, by flushing the input and having a final state, let's say, they're all equivalent. If there's a machine for one, there's a machine of the other types that does the same thing. Question up there.
You said we can use a shortcut for pushing strings onto the stack, but can you do the same thing for reading from the stack, or are you still restricted to one measure at a time?
Yeah, for reading from the stack, you should pop one at a time, because you can't say I'm going to read Shakespeare from the stack, Hamlet or whatever. Because it may or may not be there, and then if it's not there, then what did that mean by saying I'm going to read Shakespeare's Hamlet? So say I'm going to read an A, or read something from the stack and see if it's an A, rather. And then if it's an A, I'll do something. If it's a B, I'll do something else, and so on and so on. So eventually, you can encode all of Shakespeare's Hamlet in these kind of transitions, and you'll have a lot of these transitions, but it'll still be a finite state set of transitions. Delta, the transition function, will be defined finitely. You'll have a finite number of if-then-else kind of, transitions going on, and it'll eventually do the right thing. So to push, for convenience of programming, let's say you can push a fixed string, not just a character. For pop, let's just take it one character at a time so there's no confusion. But again, this is not a fundamental inherent restriction or difference. You can always do one if you do the other and vice versa. You can always handle large strings at a time in terms of pushes. And if you prefer, you can do one character at a time, for convenience or whatever works, basically. When it comes to these automata, when you program them, you don't have to worry too much about efficiency and elegance and, like you do in programming languages. But even in programming language, you don't really technically have to worry about how the code looks as long as it works. Now, this is technically in theory. Of course, in practice, the way it functions, and it's more maintainable that others, when they see it, they can understand what's going on in it. Use variable names are descriptive of what they represent, and so on. So if somebody's name is represented in a piece of code, you don't want to call it X or Z. You want to call it employee underscore name or something more explicit. Here, you don't have to worry so much about it, although even here, when you program finite automata, or if you program PDAs or even Turing machines, you can do a little bit of kind of encapsulation and kind of subroutine kind of type programming and so on, where it's not completely obfuscated. And do try to do that if you can, but usually the examples in this course will be simple and short enough so you don't have to worry about software engineering principles when you program these simple machines, because these machines will rarely get beyond 10 or 20 states, and usually there'll be 5 states or less. So that's not usually an issue. Okay, any other questions so far? let's harp on this a little more in terms of an example. So let's say I want to accept the language 0 to the n, 1 to the n, right? The language made up of equal numbers of zeros and ones, where all the ones follow all the zeros. So I want to accept 0 to the n, 1 to the n. How do I accept this language? And by the way, this language is not regular, so a finite automata cannot accept this language. And just to be precise about types, it's the set of all such strings such that n is bigger or equal to 0. I'm just putting in parentheses, in braces, so that technically it looks like a language. It's not just one big string. It's all strings of this form. All right. If finite automata cannot do this, it's not a regular language. We will prove it's not a regular language soon enough. Maybe not today, but for sure next time. If we're quick about it, we'll get to it today. It's called the pumping theorem, proving that such a thing is not a context-free language. Excuse me, not a regular language, but rather a context-free language. Okay, but it is context-free. So how will a PDA, pushdown automata, with a stack, recognize this language 0 to the n, 1 to the n? How would it do it? There's lots of ways to do it. It's not a trick question. Name some straightforward method. Yeah.
Okay, so we have one state, we've got our stack. If it's a 0, then our transition is to go back to the same state, push a 0 onto the stack. If it's a 1, our transition is to pop a 0 off the stack and go back to the same state.
Yeah. So basically you use the stack as a counter. Every time you see a 0 in the input, you push that 0 to the stack. So the stack alphabet here is the same as the input alphabet, zeros and ones. So you see a 0 in the input, you push it to the stack. See another 0, you push that to the stack. So the stack keeps growing proportional to the number of zeros that you've seen in the input. Now when you see a 1 in the input, you change your mode, go to a different state, and instead of pushing, pop a 0 from the stack every time you see a 1. So you see a 1, you pop a 0 from the stack. You see another one, you pop a 0 from the stack. In other words, you're canceling the zeros in the stack against the ones in the input, 1 to 1, pairwise. If you run out of ones in the input at the same time that you ran out of zeros in the stack that are already pushed there, you win. You can declare victory and accept that string, and you have a string on your hands that is of this form, equal numbers of zeros, the same as a number of ones. Of course, you have to make sure there's no extra ones in the input and no zeros on the stack, or extra zeros on the stack and not enough ones in the input. If either one of those conditions occur, what do? Too many zeros or too many ones, don't accept. Go to some reject state, stay there, don't do anything else, and you're not accepting that string, and that string is not in the language of that PDA. So that PDA, its language will be exactly this set of strings, equal numbers of zeros as ones where all the zeros precede all the ones. How many get this strategy? It's pretty straightforward, right? Nothing too deep about that. Questions about that? That's a straightforward example of how a pushdown automata operates. And you can recognize lots of other languages like that. What if I have a language that looks like palindromes? So I have a language that looks like WWR. And let's put a dollar sign here in between so you know where one begins and one ends. One half of the palindrome begins and one ends. I'm going to mark that middle right here. So all strings of the form WWR where W is any other string in sigma star. I'm writing it in bold so that those in the back can see it better. Okay? Might as well put the braces on it just to make sure that the type is a set very explicitly here. Hate making type errors. Okay, so how would you recognize strings of this form W, $WR, reversed? Yeah. It's W, $W reversed. So it's a string, a dollar sign, and that string reversed after the dollar sign. So if I say ABC $CBA, so CBA is ABC reversed, that's all. So WR means W reversed. Oh, that's all that notation means. It's just straightforward notation, nothing deep there. Yeah.
Clarification, is the dollar sign like any symbol from the alphabet?
So the dollar sign, let's say it's in the alphabet sigma. Excuse me. So that's a good point. So let's say, okay, I'm glad we're splitting this hair because let's call it this. So W is in A, comma B star. So sigma is A, comma B. Okay, and dollar sign is an extra symbol in the alphabet. So technically, sigma is an A, a B, and a dollar sign. 3 characters. Okay. So the dollar sign, sure, it's in the alphabet. It's got to be. Any character in any string, by definition, is in the alphabet. Otherwise, it wouldn't be that string at all. But I wanted palindromes over A's and B's and not over dollar sign. Dollar sign is just a demarcation point, the midpoint of the palindrome, and I'm explicitly entering it into the string to make your job easier to recognize such strings. Okay. Anybody want to explain how a machine would work, a pushdown automata would work that recognizes this language, W, dollar sign, WR? Let's try to have other people participate besides the same 4 people. It keeps impressing me, and I appreciate that. That's great. But I want more people in the room to participate. I hate to put anybody in the spot by calling on them, but the same 4 people keep answering every questions. You won't have a chance to feel the rush when you raise your hand and be a hero because you're asking a question or answering a question that everybody else could benefit from. So that's a good thing to do. Yeah. Mm-hmm.
And then when you hit the dollar sign, you go to the next state, and when you get an A or B, you pop up the stack, and you keep cycling on that state until the stack is complete.
Yeah. So here's a stack. Let's say you see a string of the form AAB dollar sign BAA. Right. It's getting kind of small, but so you push the W onto the stack, 1 character at a time. So you keep processing the input, pushing these characters onto the stack, A, and B, and so on. When you hit the dollar sign, what do you do? Yeah.
I'm going to say you're writing kind of high on the board up there.
Oh, I see. Okay, good point. Thank you. So I'll write this string over here. So the input string is A, B, dollar sign, B, A. Better? Okay. Is it too small, by the way? Oh, good. Okay, good. I'm glad we have these lights. Otherwise, we won't be able to see it at all. Okay, so you see the AAB, you push it on the stack. So on the stack, this is in reverse order, right? So the first A is first, second A is next, third B is last. So the last character seen is the first one on the stack. Remember, that's exactly what a stack is, kind of a reverse order. Last in, first in, last out. Right, LIFO. So once you push the AAB onto the stack, you see a dollar sign, you go into a second mode, then instead of pushing stuff onto the stack, it pops things off the stack, matching against the input characters. So now it's going to expect to see in the input the B and the A kind of reverse order, but the stack will assist you in that because the B and the A are in reverse order on the stack by nature of how the stack operates. So process the B in the input against the B in the stack. If they match, you're good. Pop the B in the stack. Then match the next one, A, against the A in the stack, and the next one, A, against the A in the stack. Pop them as you go. So you're essentially confirming and verifying that the second string past the dollar sign is the reverse of the first string that preceded the dollar sign. That it is a palindrome, in fact. How many get this strategy? It's pretty straightforward, right? Nothing too deep going on here other than checking characters against characters, making sure that they match. And you store all the characters away on the stack to begin with. When you see the dollar sign, you then start the checking state phase, process of the algorithm. Question?
So how do you exactly perform the comparison? Are you just reading from the stack? If you are, then aren't you also popping at the same time?
Well, so the transition function, remember, it takes you from a state and an input symbol and a stack element into some other state and replaces stack by whatever that is. So it's a cross product of all possible states, all possible input symbols, and all possible stack top characters. And so when you're in this you're in this popping phase, which is this Q, in one of those states, Q, and if this symbol here in the input matches this symbol here in the stack, you keep replacing that symbol with an empty string, with an epsilon, because they do match, and you keep staying in this set of transitions that keep matching and popping and matching and popping. As long as they match, you keep popping, and you're good. And if you finish processing the stack, when you finish processing the input, and everything matched in pairs, you know you got a palindrome on your hands, and then you can go into an accepting state. So you just code it all into the transition function. It's only going to be a few states, maybe 3 states or so. This whole PDA. How many get that? It'll be about 2 or 3 states, let's say, at most. Okay. Any questions about that? So now we're hacking out. We're hacking PDAs, right? Just like we hacked, finite automata using JFlap and examples from finite automata portion of the course over the last couple of weeks. Now we're kind of grinding out PDAs and making them do the right things by constructing the transitions to make the right things happen. This is programming, basically. This is primitive programming, but programming nevertheless. Yeah.
So in this case, you're the one checking if B equals A, or if whatever you pushed in equals.
It's built into the transitions function, right? The transitions function says if you're in this state and this character equals to that character, then do this. Just like a finite automata. If you're in this state and you see this character in the input that's a B, then do that. So it's like an if-then-else based on what state you're in. How many get that a transition, even in finite automata, is like an if-then-else. It's like an if-then, basically, in a programming language. If you're in this state and you see this in front of you, then do that. Go into that state. So in the programming language, if you say if this variable is equal to that value, then do this other thing. Your state in the program is where you're at right now. The program counter is where the control flow is right now. That's your state of the program, plus all the variable values that are assigned right now. How many understand that? That's the equivalent of a state in a program. And a transition is a if-then. If you're in this state and you see that condition, then go there or do this. So you see the analog between finite automata or the state transition machines in general and programming is very, very strong. In fact, programming languages are based on this. They just make it more convenient. Instead of doing this all the time with states and transitions and characters and symbols, they give you much bigger kind of more abstract constructs like sort this array by calling it library subroutine. Instead of having to come up with the 37 states that all the transitions they would take to sort the array. Question?
Yeah. So basically, like PDAs, basically it can read the top of the stack and then take action accordingly.
Yeah. So the transition function depends on not just the state like a finite automata, but also the top of the stack as well. The top character of the stack. That determines what transition happens next. Question?
Do we only get one stack, or can we do 2?
One stack. Good question. He's asking, could you have one stack or 2 stacks? Later, soon, we will discuss what happens if you have 2 stacks. If you have 2 stacks, it turns out it's equivalent to a Turing machine. You've got arbitrarily large power of computation. It's no longer just a PDA. You can do lots more things. So a PDA is restricted to 1 stack only. We'll talk a little bit more about that coming up. Other questions so far? Yeah.
You have a little file picture there with all the arrows, but what's the syntax you're writing into push and pop?
So when you answer a question like on an exam or homework, a picture is worth 1,000 words, like they say, right? So when you write a finite automata, it's better to write the states with the transitions and then an English description of how it works, rather than to do it the long, tedious, hard way with all the ordered tuples representing. That's harder to write down correctly and harder for us to parse to see if it does what you say it does. So for example, in the course on algorithms, if you say, merge sort, and you can write all the code for merge sort, but how many heard of merge sort? I don't want to be presumptuous. Good, all of you. But it's much better to have a couple of lines of pseudocode and then say merge sort basically splits the list into two equal parts, sorts each part recursively, and then merges the two sorted lists in a straightforward manner. And that's a much better description than 20 lines of code that may or may not be completely accurate, to the last character and, semicolon and parentheses. So I would much rather you drew me a picture of the transitions. This is just an abstract picture, by the way. This is not no particular PDA. But write down what all the transitions do and maybe put little descriptions of what this piece of PDA does, like pushes everything onto the stack. This transition takes care of determining the center of the palindrome by detecting the $sign, and then switching over to another mode, which is another transition over here, and then flushes the stack against the rest of the input, matching them pairwise. That description is a lot better than writing out all the gory notation that it would be equivalent to that. Okay, so I hope I answered that question in detail enough. Yeah.
What I'm asking is, given that you're writing or drawing out a little picture like that, for finite automata, it's pretty obvious what that picture does because you see all the states and you can see the transitions between them.
Yeah.
But now that you have a stack, how do you represent the commands to push and pop? You just write a push or pop above there.
Oh, I see what you're saying. Yeah. So what you can do, for finite automata, you have a state, an arrow, and another state. And on the arrow, you say something like little a, right? So that's your transition. So in a PDA, there'll be a couple more components here. There'll be an A, and on the top of the stack, if you see a B, then replace that B with an epsilon here. So there'll be three things on the arc of the transition. The character you see in the input, the character you see at the top of the stack, and what you replace it with if you take that transition. So that specifically, precisely, I think, answers that question. But you can still represent all these three things on each arc. How many get that, what we just talked about? Okay, good, excellent. Any other thoughts or questions at this point? Yeah. Let's just say acceptance by final state, never mind empty stack. You can define acceptance by empty stack instead. You can say whenever you flush the stack completely, by definition that's acceptance. That's an alternate way of defining acceptance for PDAs. But that raises the issue of sometimes you may accidentally flush the stack without intending to, just by pushing or popping whatever's on the top, and that happens to be the last character. Oops, the stack is empty. You didn't mean to accept. The stack just emptied. And so that's a little bit tricky. One way to avoid that by empty stack convention is, first thing you do before you start to compute is push, a euro sign to the stack, some character. I like to use monetary characters, euro, dollar, cents, yen, whatever. Push a euro sign, little e with a bark through it, onto the stack. And that's the first character on the stack, and that's the bottom of the stack. And whenever you see the bottom of the stack, whenever you see that euro sign, you know that there's nothing beyond that. And you never pop the euro sign unless you wanted to accept by empty stack. And then you deliberately, intentionally flush that euro sign, and then you accept. So you can always simulate acceptance by empty stack with acceptance by final state. How many get that? Okay. Straightforward. So that's why we don't harp too much on these exact conventions. Right? So that euro sign now is like end of file character in a file, like EOF. How many heard of that or used that? Right. So when you read something from a file and there's nothing to read, the program doesn't just hang or crash or complains. It returns to you this notional EOF character, and your read statement can test for that and see if you really reach the end of the input, and then you know if you need to do something else, or at least stop bothering to read more from the input, because there ain't any more there to be read, because it just returned the EOF, flag or character. Anyway, let's not harp too much on these minutiae. The point is, PDAs have a stack. With a stack, they can do more than finite automata, like recognize languages like these, 0 to the n, 1 to the n, and $WR. And that's stuff that finite automata cannot do, which means the set of context-free languages is bigger, has more languages in there than the set of regular languages. The set of regular languages is a subset of the set of context-free languages. Question: is a regular language context-free always, sometimes, or never? How many say regular language is never a context-free language? How many say regular language sometimes is a context-free language, sometimes not? All right, we got some votes there. How many say a regular language is always context-free? Okay. The majority, I think, said the latter. The regular language is always context-free. Anybody want to argue one way or the other? Like, why is a regular language always a context-free, maybe? Well, why do you say that? Why is that true, maybe? So what's a regular language? Something can be accepted by a finite automata. What's a context-free language? Something can be accepted by a pushdown automata. A pushdown automata is a finite automata with a stack. Yeah, so if you use a pushdown automata to recognize it, just never use your stack. At this point, you can do everything a finite automata can do, and you don't use this extra superpower of a stack. It's like Clark Kent, disguised as a normal reporter for the, Daily Planet. He just functions like one of us, and he doesn't fly or lift heavy things. So Superman can simulate a human. A human will have a hard time simulating Superman, especially when push comes to shove, right? So a PDA can simulate a finite automata. Just don't use your stack. Don't use your superpower. And you're good. So if you're a regular language, you are a context-free language also. How many get that? We just proved it. Just proved that every regular language is also context-free. That's the theorem we just proved. Again, because a PDA, a pushdown automata, is a finite automata with a stack. Or conversely, a finite automata is a PDA without a stack. Right? So you can say Superman is a man with superpowers, or a regular person is Superman without the extra powers of flight and super strength and so on. That's not a complicated proof. It's straightforward, right? How many understand that? So whatever a finite automata can do, a PDA can do also. Now, whatever a PDA can do, some finite automata, there are things that a PDA can do that no finite automata can possibly do, like recognize this language, 0 to the n, 1 to the n. No finite automata can do that. We haven't proven that yet. We're about to soon enough, probably by next lecture. No finite automata can recognize palindromes either. No finite automata can recognize $WR. Now, let's talk about this dollar sign here. If this dollar sign wasn't there, if this dollar sign was erased, just palindromes, plain and simple, no separator there, no dollar sign there. How many say a PDA can still recognize it, this language? Okay. How many say a PDA cannot recognize this language now? The dollar sign is missing. Okay, we have a little bit of a split vote with only a few people voting. Let me give you a hint. Or you tell me, why do you think a PDA can recognize this string? And if so, how will it do it? It doesn't have the dollar sign hint anymore where W ends and WR begins. It could be anywhere. So if I give you 1,000,000 characters and I say it's WWR, so you look at the first 500,000 characters, but you don't know what 500,000 is. You don't know where the end of the string is. So let's say I'm going to feed you a palindrome. And after 1,000,000 characters, I say, okay, we had 1,000,000 characters so far. The palindrome length, I'm not going to tell you what it is. You don't know what it is. You just look at the input one character at a time. So the palindrome could be 2,000,000 characters, in which case we just reached the halfway mark. Or the palindrome could be 1 billion characters or a Google characters, in which case we have a ways to go. But you don't know. So when do you start matching WR against a W if you don't know where one begins and one ends? How many see the problem? Okay. How do you handle that? What can you do? Yeah.
Well, if we know the length of the entire foot string, then you can divide length by
Yeah, except you don't know the length, and even if you knew the length, you have no way of doing division. Finite automata don't have a divide circuit in them. All they have is states and state changes.
say like any undefined input is each symbol for switching.
Close. Let's build on that idea. What are other thoughts? Yeah.
Can you say any time that the top of the stack is the next input, then you pop that one off?
But what if there's more and more and more input and you shouldn't have popped those because now you lost everything you pop, you kind of lose. You don't have nowhere else to store it. I'll give you all a hint. Non-determinism. One word, non-determinism. Remember I said earlier that non-determinism is essential in PDAs. There are languages that can be recognized by non-deterministic PDA that cannot be recognized by any deterministic PDA, and this is one of them, WWR. So using the idea of non-determinism, how will you recognize WWR? Yeah.
Instead of having a character to switch states, you just switch to your other state every time.
Yeah. Instead of waiting for the dollar sign to appear and then do it like you did in the deterministic case, assume it's there all the time. Every time you read another character, non-deterministically, either decide that it's the middle of the input or not the middle of the input yet, and either stay in this pushing phase or start the popping, checking phase along two different branches of the computation. And if there's a way to actually get to an acceptance state, you'll know you've seen a WWR without knowing exactly where the middle was, because you guessed all possible places for the middle to be. At any moment, you non-deterministically guessed where the middle is and branched accordingly. How many get this strategy? It's subtle, but it works, actually, because what's the definition of non-deterministic acceptance? If there is a way to get to a final state, you're good. It doesn't matter what all the non-ways not to get the final states were. It's like the venture capitalism model of computation. You fund a whole bunch of different ventures, and if one of them succeeds and becomes Google or Facebook, you're good. It doesn't matter that the other 19 things failed, right? It's the cost of doing business. It's pretty effective, right? Strategy, yeah.
Does each branch of the machine have its own stack?
So, very good question. He's asking, does each branch of the machine have its own stack? The short answer is, yeah. So it's not like there's multiple stacks simultaneously. Each branch of the computation continues with its own copy of the stack that it can independently manipulate apart from all the other branches. It's like the universe bifurcating into two parallel universes. In one universe, you do X. In one universe, you do Y. And each universe now has its own baggage associated with X versus Y decision. Right? And the two cannot interact across the two universes, but each one has a separate kind of independent existence at this point. Right? That's what non-determinism is, basically. It's like massive parallelism, like abstract, unbounded parallelism. You can keep doing this and for free, essentially. There's no efficiency cost to doing this. You don't have to pay extra for all these other stacks. Just like in the finite automata, non-deterministically branches, now you have two copies of the finite automata. Each one's in a different state, and each one accesses the input independently of all the other copies, and as long as one of them succeeds and enters the final state, you're good. So this is that plus a stack along each branch, and each stack is different than all the other stacks. But when you bifurcate, they both get the same copy of the same stack at that moment, and each one can then manipulate its own stack independently of the other threads of the computation, of this non-deterministic computation. How many understand this notion? It's fundamental. You need to understand non-determinism very, very strongly. Wrap your minds very tightly around this notion of non-determinism, because it'll come back again and again in this course. You will never see the end of it in this course. We'll mention, many times, including in Turing machines and NP-Completeness. All of NP-Completeness is based on non-determinism, actually. And we'll spend several lectures on that. Yeah.
How is having a second stack more powerful than being able to duplicate
Yeah, because non-determinism, each thread still has one stack, not two. Right? So if your alter ego in this parallel universe is a billionaire, it doesn't do you any good in this reality. It can't send you the money across the universe, boundary. See what I'm saying? So it's not like there's many stacks at the same time in the same thread of the computation. Right? It's a subtle difference, but a very important one. I hope that answered it rather than confused it even more. Yeah.
Would you perhaps optimize strategy by instead of saying you bifurcate after every character, you could bifurcate it only after you found that the current top stack value is equal to the input character?
Well, but if the top stack is equal to the input, it doesn't mean it's the middle of the string. Right? There could be many other characters that beyond that are still part of the first W.
Right, but I'm saying you would branch off into two different places. You would branch off to a place where you keep on
Oh, I see what you're saying. Yeah, you can branch only if the top of the stack is equal to the input character, which means then it has a chance to be a palindrome. Because if they're not equal, it ain't going to be a palindrome. Yeah, but that could happen a lot too. So yes, it's a very good strategy for reducing the number of times you may have to bifurcate somewhat, but not down to zero. Yeah. Okay, good, yeah. It's a nice optimization. Yeah, he's saying don't just branch blindly all the time. Branch only when it makes sense to branch, that there's a chance it'll get you to a final state and not just be not equal to a palindrome right now because the input character is not equal to the top of the stack. So there's no chance of it being a palindrome, so you might as well just stop right there and don't take that branch. Just keep pushing. Don't start popping as an alternate thread. How many understand what we just talked about? Good. It's a nice optimization, but it's not going to save you from some non-determinism and the fact that this is still a non-deterministic context-free language, only recognizable by non-deterministic pushdown automata. Now, just because something can be done non-deterministically doesn't automatically mean it can't be done non-deterministically. Excuse me, that it can be done deterministically only. This one happens to be one of those. That it can be done non-deterministically but cannot be done deterministically. And that's something you need to prove. We haven't proven that it cannot be done deterministically. It just happens to be true. The proof is not easy. So again, it's like saying, just because Superman can do something doesn't mean you can't. Superman can take his dog for a walk in the park. You can do that too. Okay? But Superman can also fly, to Mars at the speed of light, and you can't do that. Even with a spaceship, it'd be hard. So just because a non-deterministic machine can do something doesn't mean that no deterministic machine can do it. Maybe it can, maybe it can't. Maybe it's a superpower, maybe it isn't. Okay, how many get that? So keep that in mind. It's subtle. Yeah. Yeah, a good point. So she's saying if the input is odd length input, it ain't going to be one of these strings, because these strings are necessarily even. W is whatever length it is, but WR is the same length as W, and WWR is an even length string. So if the string is odd length, it ain't going to be one of those, and you can just reject it whether it looks like a palindrome or doesn't. Some odd length strings are palindromes, like ABA, for example. But they're excluded from this language by the way we define the language as a WWR. If we define it as a different definition, if we said it's W such that W is equal to WR, then ABA will be one of those. Okay. But with respect to oddness or evenness of length, it's hard for the PDA to tell if the string is even or odd without processing the whole string first, because he doesn't know where it would end. He doesn't know if it ends in 2 more characters or a googolplex more characters, because he just looks at the input character right there where the read head is on the input. It doesn't see what's way beyond that. Computations are local. They're not global. Even in your programs, the program only does local operations. How many understand that? Let me elaborate. Your program doesn't know it's looking for prime numbers. Your program doesn't know it's playing World of Warcraft with you. All it knows is that it fetches array element so-and-so, adding it to this value, storing it somewhere else, following this pointer, printing this character out to a file, reading this other character from the internet through a packet. Your program only knows these primitive operations. How many get that? It doesn't know the global picture of what's going on. That's an emergent property of your program, what it really does. So computations, all computations are just local in nature, made of very primitive atomic operations that by themselves don't make much sense and don't seem like anything useful, except you take trillions of them in combination and you got a web browser on your hands, or a compiler, or a video game, or iPhone OS 11, It's just, 100 million lines of code, each one that doesn't do much. Together, it does a lot. But the whole universe is like this, right? If you take one carbon atom and put it next to this hydrogen atom, and next to this oxygen atom, and this combination, and make a few copies of it here and there, it doesn't sound like much. But do it 10 to the 22 times, and you've got a human being. Okay? Complexity arises from simplicity, repeated many times. How many get that? It's very subtle. It's a very ubiquitous concept. It's true about all of reality, and it's true about computations. So the PDA, the finite automata, the Turing machine, they can't see the big picture. They're looking for primes. All they do is look at a single character at a time, change a single state at a time, and just go along their merry ways. And before you know it, this Turing machine is playing Second Life with you, with all the graphics that it entails. Keep that in mind. And so when you program these things, you can say, tell me if it's Shakespeare's Hamlet, or if it, even if the length is even or odd. You have to do it the hard way with atomic operations. Okay. But once you do enough of these operations, you can call them as subroutines, just like in a programming environment, and then you don't have to do everything from scratch every time. You can say, call me a sort routine to sort this array, or invoke some fast Fourier transform subroutine, or compute me a cosine or a tangent of this angle, or whatever, and same thing with PDAs, or finite automata or Turing machines. You can compose them using sort of subroutine conventions, and then you can start building up from there. You don't have to do it from scratch every time. Right? Question? Sure. On the whole, we have emergent property from all these trillions of neuron firings. That's called consciousness, right? Or personality, or self-awareness. But now we're getting at the philosophical grounds, right? Some people say these things aren't possibly a combination of little tiny atomic, trivial things. It's something like a soul, right? And we can start arguing about that ad nauseum. If this was a philosophy course, I'd be happy to do that. But right now, let's get back to finite automata and pushdown automata, so you can finish assignment number 3 that's now outstanding. Any other thoughts so far about any of this? Okay, so if a language is accepted by some context-free grammar, it's also accepted by some pushdown automata. Now, the converse is also true. If a language is accepted by a PDA, then it could also be represented by some context-free grammar. This pair of theorems, we're not going to prove here. It'll be kind of involved to prove them. But they parallel the two pair of theorems that we already saw for finite automata. Right? We said if a language is regular, or can be accepted by a regular, or represented by a regular expression, it could also be accepted by a finite automata. And conversely, if it's accepted by some finite automata, it can also be represented by a regular expression. So it's an if and only if. So the regular expressions on one hand and the finite automata on the other hand completely characterize the regular languages. So how many remember that pair of theorems? And, we had two different proofs, one for each branch of this theorem, one way, different proof for the other way. The same is true for here, pushdown automata and context-free grammars. Because the set of context-free languages can be characterized either by context-free grammars or the languages of pushdown automata. And these are two separate theorems with two different proofs. But the bottom line is you can take a context-free grammar and automatically convert it to a PDA that will accept the same language that this grammar represents or generates. Conversely, you can take a PDA, a pushdown automata, and from it work out a grammar that generates exactly the strings that the PDA accepts, no more, no less. The two proofs here are more involved in the finite automata version, and those were not trivial either, if you remember. One was a generalized finite automata and blah, blah, blah. It took a while. Here, it's probably not worth the time. But for extra credit, give me proofs for one or both of these different theorems. And if you want to take a deeper dive into this equivalence, it happens to be true. Okay. Question?
Does PDA care at all whether a language is ambiguous or not?
No. A PDA just processes one character at a time and transitions based on that character and what's on the stack. That's all it does. It doesn't know if the language is ambiguous. It doesn't know if the language consists of all the plays of Shakespeare or all the English words in the English dictionary. It doesn't know or care. It just does myopically what it's designed to do. Okay, so we have this equivalence now of context-free languages denoted either by context-free grammars or alternatively by pushdown automata, and that's an equivalence now, a twofold characterization of the context-free languages, much like we've characterized the finite automata and the regular expressions as two characterizations of the regular languages. Okay, so that's what it is. They're equivalent. So if you can do one, you can do the other for the same language. Just keep in mind that it's important that not only all the strings of one must be in the language of the other, all the strings that are not in the language of one must not be in the language of the other. So what you don't recognize is just as important as what you do recognize. Because I can recognize, a very complicated set of strings if I'm allowed to also recognize strings that aren't there. I can just recognize all of sigma star, every string in the universe, over the English alphabet sigma, by just saying yes, 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 I recognize, I accept, I accept, I accept. But that's not being very smart. A one-state finite automata can do all this. The trick is to not just recognize what you're supposed to, but also reject what you're not supposed to accept. How many get that? It's very important. It's a subtle point, but it's a very important point. So you just make sure that that is true when you design PDAs or finite automata or programs for that matter. So if a program prints out primes, it should not print out non-primes. Usually they don't tell you that in specification. It's implicit. But it's very important because if a program should print out all the primes, there's a very, very short program that does that. 2 lines of code. What is it? Start printing out all the numbers. Print 1, 2, 3, 4 all the way up. Never stop. And you'll print out all the primes. But the problem is you're printing non-primes too. So that's no big trick to do this. That's why in a court of law, they don't just say, tell the truth. What do they really say to split this hair legally? What do they say in a court of law when you're under oath? Not just tell the truth. The whole truth, and one more thing. And nothing but the truth, and they're not the same. Right? Because you can tell the truth plus pile a whole bunch of lies on top of that, and you told the truth, but you also told a bunch of non-truths. The judge will not appreciate that. In fact, you'll be guilty of perjury. Okay, so subtle point, but very important. And in the legal world, they even split that hair just so you don't mess with that, loophole, as it were, if that was available to you. Okay. Closure properties of context-free languages. Context-free languages are closed under union. Why is that true? Why are the context-free languages closed under union? If you have a context-free language and another context-free language, take the union of these two sets, these two languages, the result will also be context-free. It won't be some non-context-free language. There's plenty of those. Why does union preserve context-freeness? Thoughts, ideas? Yeah?
You'd be able to use the same union process that you did for finite automata.
Yeah, so if you try the cross-product business, you can't straightforwardly cross 2 pushdown automata. like you can cross two finite automata. Why? Why can't you cross two pushdown automata? Just have the cross product. Compute them both in parallel using some simulating pushdown automata and try to prove that the union is context-free that way. Why can't you do that? Yeah. You only have one stack. So if you simulate two PDAs and one wants to push onto the stack, the other wants to pop onto the stack, what are you going to do? You only have one stack as a simulator because you're supposed to be context-free. So you can't simulate two stacks with one stack very straightforwardly. Certainly not obvious you can do that. In general, you can't. How many understand that? So you can't just cross them blindly like you could finite automata. Finite automata, you can cross them blindly and still be a finite automata because you just have more states. But with pushdown automata, you have states and stack contents, and you can't just cross that arbitrarily. But what you can do is non-deterministically branch into one PDA or to the other PDA, and each one has its own stack, and now they don't clash anymore. Right? How many get that proof? Non-deterministically simulate both of them by branching into one or the other, and so the construction is not deterministic, but it works. Or you can use it using a grammar. You can have a new grammar that branches into the start symbol of either one or the other grammar. So you have a new grammar that basically, write it over here. So if you have one grammar, G1, that has an S in it that goes somewhere, called S1, and you have a separate grammar, G2, where you have an S2 going somewhere else, you have a new grammar, G prime, that goes to either S1 or S2, and it goes either to this grammar or to that grammar, and whatever those generate, this grammar will generate the union of all these things that these two grammars generate, and the rest of the productions remain the same. How many get this? Good. That's a lot of you. Just make sure that the variable names of these two grammars don't clash. They don't duplicate each other. And you can always rename the variables so you can do that. All right, so we'll talk more about closure properties next time. There's plenty of them, and they'll come fast and furious. Finish the homework. I mentioned in the email that you have an extra day till Saturday to do the homework, so you can go to the Saturday problem-solving session and see the TAs often and early. Take care.